Hello, it's me again. So this is the second PHYS 328 video, and what we're going to try to do today is to think more about principal axes of rotation. So let's start by just remembering what we did last time. So last time we were working on this problem where we had a square slab, and so we said the square had sides of length b, and we started with a coordinate system where we had an origin q at the bottom left corner, and we wanted to calculate the rotational inertia tensor, which we called J, with respect to point Q, where the axes were x is horizontal, y is vertical, and z is coming out of the screen. And we did that, and what we found was J was equal to mb squared, and then we had 1/3 minus a quarter, 0, minus a quarter, 1/3, 0, 0, 0, and 2/3. And so maybe the important thing to notice is that it had some off-diagonal elements. We had worked out this kind of equivalent thing that was equivalent to a parallel axis theorem for inertia tensors, and we found that we could reference to a different point, and we could connect our point Q to some other point O at the center of mass through this expression that looked like this. So I is going to have some origin O at the center of mass, and the vector A connected the two origins, so this was vector A. Okay, so if we knew the elements of J and we knew the properties of vector A, then I could figure out the rotational inertia tensor for origin O with axes that were parallel to the axes that we had for point Q. And we did that, and something nice happened. We found that when we did that, the inertia tensor that we calculated was diagonal. And it looked like this. So there's some coefficient, and then we had only diagonal terms, or elements that were non-zero. Okay, good. And what we were in the middle of doing, and we kind of ran into some technical difficulties, is we were trying to see what was the benefit of having a diagonal inertia tensor. And so I think we wrote down some of this, but let's start from here again. I may have found a way to outsmart the software if it starts acting up again. We'll see. We shall see. Okay, so this was how you would calculate angular momentum, and if we had a diagonal inertia tensor, in general, we would just have these diagonal elements I1, I2, and I3, and then omega would have its three components, omega 1, omega 2, omega 3, and if you did that multiplication, the result is fairly simple. You just get I1 omega 1, I2 omega 2, and I3 omega 3 for the three components of the angular momentum vector. Or L in vector notation is I1 omega 1 I hat. Actually, we were calling the components, or the unit vectors along the principal axes, E1 hat, E2 hat and E3 hat. Okay, then so I think that's kind of where we left off last time. We could also write down a relatively simple expression for the rotational kinetic energy. And the way we calculated rotational kinetic energy was the following. So is omega dot with the inertia tensor dot with omega again, where the omega on the left is going to be in matrix notation would be a row vector, and the omega on the right would be a column vector. Okay, but I dot omega is just L, so this is 1/2 omega dot L. And so we could simply calculate this as, let's see, 1/2 omega is going to be omega 1 E1 hat plus omega 2 E2 hat plus omega 3 E3 hat. And then we're going to dot product with L, which is I1 omega 1 E1 hat plus I2 omega 2 E2 hat plus I3 omega 3 E3 hat. Okay, and then evaluating the dot product, all of the unit vectors are perpendicular to one another, so the only terms that survive are like E1 dot with E1, E2 dot with E2, and E3 dot with E3. And so what comes out is 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared plus 1/2 I3 omega 3 squared. Okay, and again, it's still a relatively simple expression compared to what you would get if you had off-diagonal terms. So there was one other thing that I wanted to do in the last video, and I wanted to see what would happen if the body that we're considering is rotated about one of the principal axes. Okay, so as an example, we could say that our omega vector, our angular velocity, is along, say, the first principal axis. And then omega 2 is equal to omega 3 is equal to 0. Well, in that case, if we just go back to our calculation of L, and we say, well, what we're going to do is we're going to say omega 2 is 0, omega 3 is 0, so that these two terms are 0. And what you're going to end up with is omega 2 is 0, omega 3 is 0. You're just going to end up with a single term in your calculation of L. And that single term would look like I1 omega 1 E1 hat, but omega 1 E1 hat is just the omega vector, and so we get I1 omega. And so that's really simple, and more than being simple, what we can observe is L is in the direction of omega. So here's an important observation. So an important fact, let's call it. If the body is rotating about one of the principal axes, then the angular momentum L will be in the same direction as omega. So if body is rotating about one of the principal axes, oh, that's fun. of the principal axes, then L is in the direction of omega. Otherwise, if the body is not rotating about one of the principal axes, L is not going to be in the direction of omega. It may have a component in the direction of omega, but it will have other non-zero components. Otherwise, L is not in the direction of omega. Okay, good. So, I want to think back to, I guess it would have been the last in-person class, and we were still working with this square slab. Let me draw it again. So X and Y, and here's our slab, sides of length B. And what we did is we calculated the angular momentum for a rotation along the diagonal. So we took a rotation axis that was along this diagonal here, and so we spin our slab around that rotation axis. And we found in that case that the angular momentum was in the direction of the omega vector. And so omega is going to be in that direction. So we previously found for our square slab that when rotated about the diagonal, L was parallel to omega. So we'll just go through and we'll just confirm that once again as a bit of a review. So in this case, omega is going to be some magnitude or some length, and then it's going to have components along x and along y. Okay, so let's just calculate. L is, I guess it's going to be J is what we're calling it now if we have a point here where our origin is Q. So J dot omega, and J was equal to, so let's go back over here, we had along the diagonal 1/3, 1/3, 2/3, and two off diagonal elements that were -1/4. So we're going to get mb squared, and we'll have 1/3 -1/4, 0, -1/4, 1/3, 0, 0, 0, and then 2/3. And then our omega vector is going to be omega over root 2, and then we're going to get 1, 1, 0. Okay, so if we do that matrix multiplication, we get mb squared omega over root 2, and then we get 1/3 -1/4 for the first entry, and then we get -1/4 plus 1/3 for the second entry, and then we get 0 for the last element, the last component of L. So 1/3 -1/4 is 4/12 minus 3/12, and so that's 1/12. And what we end up with is mb squared omega 12 root 2 in the denominator, and then 1, 1, 0. But omega times 1, 1, 0 is the original omega vector with the root 2 factor. And so this is equivalent to mb squared over 12 times omega. Okay, in other words, L and omega are in the same direction. What I'm going to do is I'm going to write this as, let's write as L equals I1 times omega, where I1 is going to be mb squared over 12. So what we just said at the beginning was that if we could find an axis for which L and omega are parallel, then that axis must be a principal axis. So the diagonal must be a principal axis for our square slab with an origin Q at the bottom corner. Well, I mean, it's symmetric. It could be any corner, I guess. Must be a principal axis for an origin Q at the corner of a square slab. Okay, so we kind of, almost by accident, have found one of the principal axes. If we could actually identify a second one, then we would know all three of the principal axes because they have to be mutually perpendicular. So if we have two of them, there's only one choice for the third, and we would know everything. Okay, so let's see if we can check another case. The other case we're going to check is for the z-axis. Say omega is along the z direction, which is out of the screen. So let's check omega equals some scalar amplitude, and it's in the k-hat direction. So if I calculate L in that case, I'm going to get mb squared, and then we'll pick up the omega when we do the dot product with the omega vector. And then our square matrix is 1/3 minus 1/4, 0, minus 1/4, 1/3, 0, 0, 0, 2/3. Okay, and then omega has just one component, and that's the z component. And so here the matrix multiplication is pretty easy because we get zeros initially. We get 1/3 times a 0 plus minus 1/4 times 0 plus 0 times 1. And so the first element is mb squared omega 0. For the second element, we're also going to get 0. And for the third element, we'll just get 2/3. Okay, but that's just equal to let's do 2/3 mb squared omega times 0, 0, 1, but that's just the omega vector, and so therefore L is equal to 2/3 mb squared omega, And let's do it like we did before. Let's say I'm going to choose this one to be, I'm going to label it as I3. Okay. And so we could write this then as L is equal to I3 times omega. So it must be the case that Z is also a principal axis for the square slab with origin Q at a corner. Therefore, the Z-axis must also be a principal axis. All right, so if we draw the square slab again, and we started with, you know, a regular X, Y, Z coordinate system. Sorry, that's going to be our y-axis. And our z-axis is going to be coming out of the page towards us. So there's z is out of the screen. Okay, so what we found is if we chose a diagonal, then we found that that was a principal axis. And so I'm going to label that as the E1 axis. We found also that the z-axis is a principal axis, and I'm going to call that the third axis. So one of the principal axes is coming directly out of the screen. So what we have to do in order to find the third one, which we're going to call E2, is to just make it perpendicular to E1 and to E3. So if it's perpendicular to E3, which is out of the screen, it must be in the plane of the screen. So that's good, so we can draw it. And then it just has to be perpendicular to E1. And so let's make this choice, where this is going to be now E2, and this is a 90-degree angle. Okay, so if we know two of the principal axes by whatever means possible, then the third is perpendicular to both. So therefore, we have deduced that this E2 axis is in the direction given by, say, n hat is, well, how did we draw it? It has a component along the positive y-axis towards the top of the screen. So there's going to be a plus, say, j hat. There's no z component because it's in the plane of the screen. But then it has a component in the negative x direction, right? And so we put in a minus I hat. Okay, so that might be right. Let's check it out. Let's check if L is parallel to omega when omega is equal to some amplitude times n hat, which is going to be omega over root 2 minus I hat plus j hat. Okay, so what do we get? L is mb squared. When we multiply by omega, we'll pick up the omega over root 2 factor. And then we have 1/3 minus 1/4, 0, minus 1/4, 1/3, 0, 0, 0, 2/3. And so now we have a component along minus x and plus y, but nothing along z. Okay. mb squared omega over root 2. And so we get minus a third plus minus a quarter. Minus a third plus minus a quarter. And for the second component, we have minus a quarter times minus 1, so that's plus a quarter, plus 1 times a third, plus a third, and then we get 0. So let's see, a quarter plus a third is, what, 3/12 plus 4/12, 7 over 12. Okay, so this is equal to 7 mb squared over 12, and then I'm going to write this as omega over root 2, and we get a minus 1, a plus 1, and a 0. But this is exactly the original omega vector, and so we get that L is equal to 7 mb squared over 12 times omega, where this is what we'll call, I should say, I2. Okay, so L is parallel to omega, and as expected, principal axis E2 is in the direction that we said with n hat. N hat was 1 over root 2 minus I hat plus j hat. All right, good. So now we know the 3 principal axes for our square slab with origin at Q. And furthermore, we know the rotational inertia, I1, I2, and I3. Let's just collect them all in place here. So I1 was, if we remember, it was 1 over 12. And that was the diagonal. I2, we just calculated, it's 7 over 12 mb squared, so I forgot my mb squared over here. And then I3, which is the z-axis, was 2/3 mb squared. You can see this makes sense. The I1, the diagonal axis, is the smallest rotational inertia. And that makes sense because that's where we have an axis with a lot of the mass close to that rotation axis, and so a relatively small rotational inertia. All right. So we could, therefore, construct a diagonal. So I'm going to, a diagonal inertia tensor, I'm going to put a little subscript E on the J, just to indicate that this is the one that corresponds to our principal axes. So it shows a coordinate system with origin Q, but we selected axes not to be horizontal and vertical, say with respect to the edges of the square, but to be the principal axes, one of which is a diagonal. So this is 4 point Q referenced to the principal axes, E1, E2, and E3. So it's mb squared, and then it's just going to be I1, 0, 0, 0, I2, 0, 0, 0, I3, or it's mb squared 1 over 12, 0, 0, 0, 7 over 12, 0, 0, 0, and 2/3. So what we've got now are two different inertia tensors for point Q, one corresponding to the axes x, y, and z, which has some off-diagonal elements, and then one corresponding to the principal axes, which is diagonal. Now it must be that if I rotate my object in a particular direction, say omega is equal to, the omega vector is along the x-axis, I must calculate the exact same angular momentum whether I'm using the rotational inertia tensor for the XYZ system or whether I'm using the rotational inertia tensor for the E1, E2, E3 coordinate system. And so what I'd like to do is I'd like to verify that that is in fact true. Before we do that, what I'm going to try to do here is to switch to a new screen in an attempt to prevent this thing from being slow to respond. So let's see how well this little trick works. Of course, it must be the case that the L we calculate for a particular omega will always be the same regardless of the choice of coordinate system. Now we're going to find that it's always more convenient to work in a coordinate system that are the principal axes, but we don't have to do that. So I want to do a little verification calculation. Let's check with omega is along the x direction. Okay, so as a picture, what we've got is an xy axis, and here's our square slab, and then we've got an E1 axis and an E2 axis, like so. And then, of course, there is a z-axis. It's coming out of the page, and that's also the E3 axis. Okay, so what we're imagining is that we've got an omega vector that is along the z-axis. And so if I want to compare the angular momentum calculated from two different reference frames, I need to be able to write omega in terms of components along the E1 and E2 axis. So in fact, what I'm going to do is I'm going to extend this E2 axis downwards. And we're going to label in here that we've got an angle alpha and an angle alpha, where alpha, in this case, if E1's a diagonal of a square slab, alpha is pi over 4. Okay, so if we break this omega vector into components along E1 and E2, what you can see is that what we've got is here, if this is length omega, this is a length omega over root 2, and this is also a length omega over root 2. Because alpha is pi by 4, and what we would be calculating are cosines of alpha, and cosine of pi by 4 is 1 over root 2. Okay, so in terms of components in the E1, E2, E3 coordinate system, omega is equal to omega over root 2, and then we have a component along E1, so we have a E1 hat, and then we have a component that's along minus E2, so we have a minus E2 hat. Okay, good. So we have our two omega vectors in our two coordinate systems. So let's start with the XYZ system. XYZ system. L is going to be equal to J dot omega, which is going to be mb squared. We'll pick up a factor of omega. And then this is the tensor that has the off-diagonal elements. And then omega is simple in this coordinate system. It's just along z. Along x. Okay, so that's mb squared omega, and then we get a 1/3, and then we get a minus 1/4 for the second component, and then a 0. Okay, so we could write that, I guess, as mb squared omega. Let's put a 12 out here. And so we'd get 4 and minus 3. Okay, so that is the angular momentum in the XYZ system. So let's do the E1, E2, E3 system. So L is going to be, remember we labeled this as J sub E to remind us that these were the principal axes, and then we have dot omega. Okay, so our diagonal inertia tensor was mb squared, and then we had 1 over 12, 0, 0, 0, 7 over 12, 0, 0, 0, 2/3. And now omega, here, it's just up here, is omega over root 2, and then it's plus in the E1 direction and minus in the E2 direction. So we should get omega over root 2, 1 minus 1, 0. So this is mb squared omega over root 2. And what do we get? This is pretty simple, actually. So we get 1 over 12, and then we get minus 7 over 12, and then 0. which is mb squared omega 12 over root 2, 1 and minus 7 and 0. Okay, so we have two results for the angular momentum in the two different coordinate systems. And I mean, if you look at them, they look different. But remember, this is in terms of components Lx, Ly, and Lz. And this is in terms of components let's say LE1, LE2, and LE3. What we might try to do is we might try to see, are these in fact equivalent angular momentum? They better be, or there's a problem, because that would tell us that we get different answers depending on what coordinate system we chose. So let's see if we can do this. So I'll draw an xy coordinate system. All right. And in the xy system, the angular momentum is, some prefactor, but then it's 4 units along x and minus 3 along y. So we'll take 1, 2, 3, 4 units along x and 1, 2, 3 in the negative y direction. Okay, so that means L is going to look something like this. So this is our L vector in the xy system. Okay, and let's see, E1 is along the diagonal, and then E2 is perpendicular to that, and let's see, the diagonal would be something like this. This is going to be E2, and so I'll extend it backwards this way. Okay, good. So what we are going to try to do is we're going to try and re-express L, which we'll start with it in terms of xy components and rewrite that in terms of E1 and E2 components. So one thing we're going to need is this angle, which I'll call phi. So the angle phi, the tan of that angle, is the opposite, which is 3 units, right? 1, 2, 3 along the y direction, over adjacent, which is 1, 2, 3, 4 in the x direction. So this is 3 over 4. And so if you take your calculator and figure out what that angle is, it's like 36.9 degrees. Okay. So let's see if we can find an E1 component. So I'm going to try and draw this back here so that this makes a right angle. All right, and the E1 component is this vector. So this is L E1. Okay, and the E2 component is this vector. This is L E2. Okay, so the angle in here Sorry, that's not the angle that I want. I want, let's see, I want this angle. Because if I knew that angle, so let's suppose I call it theta, then I could write that LE1 is the side adjacent to this angle theta, and the hypotenuse is a length of L, the magnitude of our angular momentum, and so this is going to be L cos theta. Okay, and likewise LE2 is going to be the side opposite of theta, and so that's going to be sine of theta. Okay, but we know that between the x-axis and the E1 axis, we have 45 degrees. So theta must be equal to 45 degrees plus phi, which is that 36.9 degrees. And if you add those two up, you get 81.9 degrees. Okay, and so let's work out the magnitude of L. The magnitude of L is going to be the x component squared plus the y component squared, all square root. And so that's going to be mb squared omega over 12, and then we have a 4 and a 3. So this will turn out to be mb squared omega over 12 square root of 4 squared plus minus 3 squared. So that's 16 plus 9 is 25, square root is 5, and so this comes out to be 5 mb squared omega over 12. Okay. So LE1 is L 5 over 12 mb squared omega, and then it's the cosine of 81.9 degrees. And if you punch in the numbers, this comes out to be 0.0589 mb squared omega. And if you compare this to 1 over 12 divided by root 2, you get exactly the same number. So this is equivalent to 1 over 12 root 2, so that LE1 is going to be mb squared omega over 12 root 2. And if we go back to this calculation, the first component, the one with the 1 here, had a 12b squared omega over 12 root 2. And so we've successfully shown that the angular momentum, although expressed in different, as components of different coordinate systems, were equivalent, at least for the E1 component. Of course, the E2 component is going to work as well. E2 is going to be, let's see, let's not forget that there's a minus sign, because for LE2, the big green vector points along the negative direction of the second principal axis. So we have a minus L sine theta. So what I should have had up here is I forgot my minus sign. So we'll fix that. Okay, L we already know is going to be 5 over 12 mb squared omega. And then we have the sine of 81.9 degrees. And again, if you punch that into your calculator, what you're going to get is minus 0.412 mb squared omega. And this 0.412 is the same thing as 7 over 12 root 2. And so this is minus 7 over 12 root 2 mb squared omega. And that's also what we calculated right here. So there's that minus 7 factor is right there. So what we've done then is we've managed to confirm. So we have confirmed that we can work with whatever set of axes we want with origin Q and calculate consistent results. It's just much more convenient. Ooh. So it's just much more convenient to use a set of principal axes, because the expressions for things like angular momentum and rotational kinetic energy become much more straightforward. Okay, now what I want to do is I want to do a calculation that was similar to one that we did in the last video. And so we're going to start with an inertia tensor for origin Q that corresponds to the principal axes. And then we're going to use the generalized parallel axis theorem to determine what the rotational inertia tensor would be for a point at the center of mass, an origin at the center of mass. So next, let's start with axes E1, E2, and E3 with origin Q, and with origin Q, oh, you son of a... We'll try this one more time, and then I'll see about starting a new screen. With origin Q, and use the generalized parallel axis theorem to move to a point at the center of mass. Okay, so let's draw a picture of what that looks like. So we got our square slab of sides B, and we have our axes, our principal axes, E1 and E2, and E3 is out of the screen. Here's our point Q, and we know the inertia tensor for this point and this set of axes. And then what we're going to do is we're going to go over to the center of mass here, and we're going to say, let's find the rotational inertia for a point O, which is at the center of mass. Now the axes that we're going to end up working with are going to be parallel to the axes we started with. So they'll be along the diagonal, and there'll be one that's coming out of the screen. So this is point O at the center of mass, and we're going to calculate the inertia tensor, and I'm going to label it IE. Okay, the vector A that connects the two origins is this vector. So this is vector A. So let me remind you what the generalized parallel axis theorem looked like. We did write it down, I think, at the beginning, but let's repeat it. So what we're going to try to do is we're going to try to calculate the elements of IE. And so it'll have two components, I and j. So we'll start with the elements of the j tensor, and then we'll have to subtract the mass, and then there was an a squared delta ij, and then there was a minus ai aj. Okay, so what's nice about this is that the a vector, in terms of the principal axes, is pretty straightforward. A is just exactly along the E1 axis. Its length is b over root 2, because if we go down here, this length is b over 2, and this length is b over 2, and so the length of A is b over 2 squared plus b over 2 squared square root. So that's b squared over 4 plus b squared over 4, which is b squared over 2. Take the square root, that's b over root 2. Okay, good. And so when we use this generalized parallel axis theorem, we're going to want the individual components of A, and so we say there's only one component, and it's A1, and it's b over root 2. That means the A2 and the A3 components are 0, and we'll also need the length of A squared, which is just going to be b squared over 2. Okay, so with that, we can then start our parallel axis theorem calculation. And oh, what happened? Did we lose? I don't know what happened. There was okay, anyways, so maybe let's keep that up in the top corner there just for a second. So let's start with the 1, 1 component. So JE11, let's go find that. Oh, here it is. MB squared over 12. Let's just remember that the 2, 2 component is 7 over 12, and the 3, 3 component is 2/3. So 7 over 12 and 2/3. Oh, what happened here? Got to. Okay, we'll worry about that later. Okay, so it was MB squared over 12. So MB squared over 12. And then we have minus M. And we have delta ij. For the 1, 1 component, that's delta 1, 1, which is 1. So we have an a squared, which we said was b squared over 2. And then we have a minus a1 times a1. So a1 is b over root 2, and a1 is b over root 2. So all of this combines to be just a 0, and we get that the 1, 1 component of IE is going to be mb squared over 12. Okay, let's do the 2, 2. So we remembered that that was going to be 7 over 12, right? Minus m. We'll get a b squared over 2 because we have a delta 2, 2, which is 1, and then we have an a squared. But then we're going to have an a2 times an a2. But those are both 0. And so what we get is, let's see, mb squared over 12. And then we have a 7 minus 1/2. But we're going to write that over 12, so it's 7 minus 6. And so that's going to be just mb squared over 12. Okay, I33. So that one was 2/3, right? So that was 2/3 mb squared minus m. We have an a squared minus an a3 times a3, but a3 is 0. So what do we have? mb squared, let's put it over 6. So 2/3 becomes a 4/6 minus, this should be a 2. So 1/2 becomes 3/6, so 3. And so this is mb squared over 6. Okay, so now we have all the off diagonals. I12 is the same as I21. And so what we need to first do is to take the off diagonal of j, but j has no off diagonals. So it's 0 minus m times, it was a squared delta ij, but now I is 1, j is 2, delta ij is 0. So then we have minus a1 times a2. a1 was b over root 2, but a2 is 0. So we're just going to get a 0. And we get 0 for that off diagonal. You might be able to see that we're going to get 0 for all of these off diagonals. Because j has no off diagonals, the delta function is 0, and then we have a minus aj, but for anything other than a1 times a1, we're going to get zeros. So if we have an a3 in there, we'll get a 0. Okay, and then the last one is the 2, 3, and the 3, 2. And so we'll get 0 minus m times 0, which is 0. We have no off diagonal elements. So when we construct our inertia tensor, what it has is mb squared over 6, and then we had a 1/12, so I'll write that as a 1/2, 0, 0, 0, 1/2, 0, 0, 0, 1, and so it's diagonal. And that must mean that this coordinate system at the origin of the square slab with principal axes, well, with axes along the diagonals and one out of the screen, is a set of principal axes. Okay, so therefore we have found a set of principal axes. And so if I draw that picture, we've got our square slab. Oh, I can make it more square, I think. Oh. So here's the center of mass. This is where our origin O is. And we've determined now that these red axes are principal axes. There's one out of the page as well. So the red axes are principal axes. They must be, because we've just written down the inertia tensor for this set of axes with origin O, and it's diagonal. But you may remember that in the last video, we found a different set of principal axes for the same point. Last time, we showed that the blue axes were principal axes. And so therefore we can only conclude that there must not be necessarily a unique set of principal axes. You could have a shape and an origin that has multiple different sets of principal axes. Oh, I just want to write down one sentence, so let's see if we can do that. Uh-oh. So I think we're in trouble here. It's frozen. I can't do anything. Let me try one thing here. Okay, good. This will work. I'm doing the best I can, but this software has its limitations. Okay, good. I think the trick of using multiple screens worked. Maybe I'm going to need to use more like 3 or 4 sets rather than just 2. So evidently there does not have to be just a single set of principal axes associated with a given origin. Okay, good. So that's it for today. If anyone's still listening, you can leave a comment on the YouTube page that you made it to the end. Before making this video, I made one for the 216 class, and I discovered that I made the whole video without having the microphone turned on, and so that was a nice surprise. Anyways, so I hope the audio got recorded in this video, and we'll talk to you again shortly. Thank you.